Hey everyone, how are you? In this video, we are going to solve the Leetcode problem of the day, and the problem is count square submatrices with all ones. The problem category is marked as medium, but we are going to solve it in a very easy way. The input given in the problem is a m by n matrix of 1 or 0. So we are given a two-dimensional data or a two-dimensional array of m number of rows, n number of columns, and all the elements in this 2D array will be 1 or 0. The output we need to give is the number of square submatrix of all ones. Let us try to understand the problem with an example. Let us say that this is the given two-dimensional data or two-dimensional matrix. So you can imagine that this is a 2D data. So we have a two-dimensional data and each row itself is an array. And now we have a m by n matrix or m by n 2D array. M number of rows, n number of columns. Now, first of all, we need to understand how can you find the number of rows and number of columns. So basically, if you see your two-dimensional array, the length of your two-dimensional array is the number of rows. We have 1, we have 2, we have 3 number of rows. How can you find the number of columns? You can pick any row because all the rows have same number of data. So you can pick any row and count the length of the element in any row, and that is going to be the number of columns. So let us pick the first row. This is the row and the number of elements are 1, 2, 3, 4. So we have 3 number of rows and 4 number of columns, right? The output for this particular input is 15. Now what is this output? It is the number of square submatrix which contains all ones. Now what is a square? It is a very easy term, right? Any data that has the same width and same height is a square, right? If you have a square, then the width and height is going to be same, right? Now when we talk about the square submatrix, it is like saying that a submatrix or a matrix which has dimensions as same number of rows and same number of columns. And when we say submatrix, it is like picking up some elements from your two-dimensional array and creating a square out of it. For example, I can say right now I have a 3 by 4 matrix, right? 3 number of rows and 4 number of columns. I can say that if I pick these 4 elements and call it as a submatrix, then this is a 2 by 2 square submatrix. Why this is a square submatrix? Because the number of rows and the number of columns are same. So we just need to find out how many square submatrix we have which contains all ones. So the square submatrix dimension can be 1 by 1, that is 1 row 1 column, or 2 by 2, that is 2 row 2 column, 3 by 3, that is 3 row 3 column, right? So we can say d by d, that is d number of rows and d number of column is a square submatrix. Now this particular data has an output as 15. Let us count the output and then we are going to understand the approach to solve it. If you just pick one element, then this is a square submatrix of all ones. It has just one element which is 1, right? So it has all ones. And why this is a square submatrix? Because it has one row and one column. So the dimensions are 1 by 1. You have just one element and that has one number of row and one number of column, right? One row, one column. So it is a square submatrix. So from here we can say that every element which is a 1 is a square matrix of all ones. So we have total 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We have a total of 10 square submatrix which has all ones and the dimensions are 1 by 1. One row, one column. But we can have more number of square submatrices. It can be 2 by 2, right? Or 3 by 3. That is 3 number of rows, 3 number of columns, 2 number of rows, 2 number of columns. Now, if you notice at this particular data, if you consider this as a submatrix, then it has 2 number of rows and 2 number of columns. So it is a square submatrix. It has all ones. So it is a square submatrix with all ones. So we can count this as well, right? We counted individual elements as a square submatrix, but now we can count this as a square submatrix as well. So let us count all the square submatrix which are of the size 2 by 2. So I can say that this is a square submatrix of 2 by 2, right? I got one. Now we have more square submatrices of size 2 by 2. We have this as well. The size is 2 by 2 and all ones. Apart from this, we have this as well. The size is 2 by 2 and all ones. And we have one more 2 by 2 square submatrix, which is this one. 2 by 2, all ones. So we got 4 number of square submatrix of size 2. That is, it has 2 rows and 2 columns. And we have one more square submatrix which has 3 number of rows and 3 number of columns, and all the elements are 1 here, right? So we got one more which is a 3 size, that is 3 number of rows and 3 number of columns. So now we have total of 10 plus 4 plus 1, which is 15 number of square submatrix for this particular data. Now let us understand the solution approach. First of all, if I talk about a square submatrix of dimension 1, that is 1 row and 1 column. So what we can do is we can see that check each element in our matrix. If that element is a 1, then we can say that we have a 1 by 1 square submatrix containing all ones. Basically, this is also a square submatrix where we have just one element, and we can say that we have one element which has one number of row, one number of column, but the elements are 0. We want square submatrix of all elements as 1. So we can go through the entire matrix and we can say that anything which is a 1 can be counted as a 1 by 1 square submatrix, right? Now what about 2? What about the square submatrix of size 2? Let us consider this one. This is a square submatrix of size 2, 2 rows, 2 columns. But we are not going to count it, and the reason is it has a 0. But we are going to count this one. Now first of all, tell me, how can you identify that this is a square submatrix, this is a square submatrix, but this is not to be counted and this to be counted? It is very simple. If your square submatrix has any 0, then we are not going to count it. That is one of the approach. But here you will have to find all the 2 by 2 submatrix, 3 by 3 submatrix, 4 by 4 submatrix, right? And then you will have to go through the entire elements to check that do we have a 0. If we have a 0, we don't count it. If we do not have a 0, we count it. There is another approach to solve it. Imagine about this. This is a square submatrix. Now, how can I verify that this square submatrix is a 2 by 2 square submatrix? I know that we have 2 rows, 2 columns, but how to verify this? See, the simple thing is, if I am at this particular element and I want to check for this particular square submatrix, and if this is a 1, this has to be a 1, right? If I am at this element and it is 0, then we don't need to check for this particular square submatrix because this element itself is a 0. For example, if this is a square submatrix and I am at this particular element, it is 0, then whether all the elements are 1, since it is 0, it is not to be counted. When we talk about this particular subarray or submatrix, I would say, and we are at this element, now to verify that this is a 2 by 2 square submatrix, we can say that this element has to be a 1, the upper element has to be a 1, the diagonal element has to be a 1, and the right element has to be a 1. If all the other 3 elements are a 1, I can say that this is a square submatrix of size 2 by 2. Similarly, for this particular subarray, which is a size of 3 by 3, how can we verify? I will look at this element, or let us say we look at this element. So I can say that this has to be a 1, and the 2 upper elements has to be 1, the 2 diagonal elements has to be 1, the 2 right elements has to be 1, right? And we have to verify these 2 elements as well. Now this process of checking each element in your square submatrix is going to be complex, but there is another process to verify it. Let me tell you how. Now let's go element by element. If I am at this particular element, it is 0. Let's ignore this completely. If I am at this particular element, it is 1. It can form a square submatrix of 1 by 1 or 2 by 2 or 3 by 3, any length, right? Basically this element is contributing to a 2 by 2 matrix, which is this one, and a 3 by 3 matrix, which is this one. This element is contributing to it, right? But how can we verify this? See, the simple thing is, let's go element by element and let's do the verification. If I am at this particular element, I will say that this can be a 1 by 1 submatrix, right? So we are going to count it because it is a 1. Now can this be a 2 by 2 submatrix? We are going to check the upper element, the left element, and the diagonal element. But since it is the first row, it is not going to have upper element, not going to have a diagonal element. It is going to have a left element, but it is not going to have upper and diagonal element, right? Basically what I want to tell you guys is, if we talk about this particular submatrix and we just see the last element of this, if it is a 1, then we will start our verification that what size it can become. So we can check its upper element, its left element, and its diagonal element. Basically when we are at this one, the upper element is 1, the left element is 1, the diagonal element is also 1. So it is telling me that this particular element can be a part of 2 by 2 submatrix, and that is a square and all ones. So I can say that this can be a 2 by 2 submatrix just by looking at this element and verifying it with upper, left, and diagonal element. We can do the same operation with all the elements, and let me show you how. See, the thing is, the first row element are not going to have upper element, and the first column element are not going to have left element. So let us process the first row and the first column separately. Let us focus on other elements which can have upper, left, and diagonal elements as well. We are just going to focus on this particular data. Now this is the first element, right? Now I know that this is a 1. It means that this element is contributing to one square submatrix of size 1 by 1. But can this contribute to bigger size submatrix? We are just going to look up, look left, and look in the diagonal. The up is fine, left is fine, but the diagonal is 0. So this particular element can be the last element of a square submatrix of size 1. It cannot be the last element of the square submatrix of size 2 or 3 or 4 or any bigger size, because it has an element which is a 0 in the diagonal, right? If this would have been a 1, then we would have said that okay, the upper is fine, left is fine, and the diagonal is fine. So this element can be a part of, or can be the last element of, a bigger square submatrix. And what should be the size? If this would have been 1, then the size would have been 2 by 2, right? A square submatrix of 2 by 2. Now how can you find that this can be a 2 by 2 and not 3 by 3 or 4 by 4 or 5 by 5? Because if we look at this particular square submatrix and look at the last element, this is the part of 3 by 3 submatrix, right? How can I find that this can be a part of 3 by 3 submatrix, this can be a part of 2 by 2 or 1 by 1? See, the simple thing is, just process each element look up, look in the left, look in the diagonal. What is the minimum you have got? The minimum you have got is 0, right? If it is a 0, then you can be a part of minimum plus 1 square submatrix, the size of 1. This element can be the last element of a square submatrix of size 1. We are going to verify the same for other elements as well. So this will be 1 as of now. What about this one? Again, we are going to do the same operation. For this element, look up, look in the left, look in the diagonal. All are 1, right? So this can be a part of, or this can be the last element of a square submatrix of size more than 1, right? And what will be the size? What is the minimum of these 3 elements? The minimum is 1, right? Now, if the minimum is 1, then this will be 2. Basically, minimum plus 1, which is 2. And let me tell you why. First, let me put it as 2. Now, when I say that this is 2, it means that this element can be the last element of a square submatrix of size 2. Basically, this is the square submatrix. How can we say this? If this was 1, it is a square submatrix of 1 by 1 for sure, right? Now the upper elements and the left and the diagonal elements are 1 as well. So now this can be a part of a bigger submatrix of size 2. Now these are 1s, right? If this would have been 2, why this can be a 2? If the upper is 1, the diagonal is 1 and the left is 1, right? Why this element will be a 2? When the upper is 1, left is 1 and diagonal is 1, right? Then only this will be a 2. And why this element can be a 2? If the upper is 1, if the left is 1 and the diagonal is 1, then this can be a 2. Now for this element, if the upper, left and the diagonal is 2, then the minimum is 2. So I can say minimum plus 1, which is 3. So now this element is the part of 3 by 3 submatrix. And basically this is our submatrix, which is of 3 by 3. This is how we are creating the answer for each element. Now the thing is, guys, this is a simple implementation of DP, dynamic programming. The reason is, for this element, we are utilizing the answer of previous elements. That's what dynamic programming is all about, right? Now, when I say that this is a 2, it means that this element is contributing to 2 different square submatrices. Basically, it was originally 1, right? So it is contributing to a 1 by 1 square submatrix. That's 1. And now, if I say that this is a 2, so it is contributing to 2 square submatrix. One, the element itself. And now I say that this is a 2, then this particular square submatrix as well. This is also we need to count, right? So when this is 2, we are going to count it as 2. Because if it is 2, then the elements would be 1, 1, 1, 1, right? This element itself is a square submatrix and this is another square submatrix. Total 2 square submatrix. Now what about this? Again, we are going to do the same operation. The upper is 1, the diagonal is 1, the left is 2. What is the minimum? Minimum is 1. Minimum of all these 3 elements is 1. So 1 plus 1 is 2. It means that this particular element is creating a square submatrix of size 2. So let me make it as 2. Now, when I say that this is a 2, it means that it is contributing to a total 2 different square submatrix. It was originally 1, right? So one square submatrix will be the element itself of size 1 by 1 and one square submatrix of these 4 elements. Basically, we are just saying that this is the last element of our square submatrix. The last element means the last row, the last column. So when this is 1, and I'm saying that this is a square submatrix of size 2, this is the last element of that square submatrix. So we are basically talking about this. So we are going to count this as 2. Similarly, for this one, what is the minimum of all these 3 elements? The minimum is 0. It means that this particular element is going to contribute a total of 0 plus 1, minimum plus 1, which is 1 square submatrix, and this 1 square submatrix is the element itself, because this is a 0, right? If this would have been a 1, then we would have created it as a 2 by 2 submatrix, and this element would contribute to total 2 square submatrix, right? So this will be 2, but since it is 0, so we are going to say that the minimum plus 1, which is equal to 1. Now what about this? For this element, the upper is 2, diagonal is 1, left is 1, minimum out of these 3 elements are 1, and we are going to say minimum plus 1, which is 2. So this element will be changed to 2, and what we are saying that this element is the last element of a 2 by 2 square submatrix. So this element is contributing to total 2 square submatrix. Now let us focus on the last element, which is 1, right? Now let us look up, left and diagonal. The minimum is 2, right? If the minimum is 2 and applying the same formula, minimum plus 1, which is 3, so we are going to replace this element with 3. So what we are saying that this element is the last element of a 3 by 3 square submatrix containing all 1s. So this is going to contribute a total of 3 different square submatrix. One of size 1 itself, the element itself, one of size 2, one of size 3, right? And now you will see the magic of this particular calculation. If I say 3 plus 2 plus 1, it is 6. 2 plus 2 plus 1 plus 1 is 6. And 1 plus 1 plus 1 is 3. 6 plus 6 plus 3 is 15. So basically now if you count each element in your data, it is the total number of different square submatrix containing all 1s. So now this is the way to solve this particular problem. Now how can we do this technically using programming? See, the thing is, first of all, we are going to find the number of rows. The number of rows are going to be the number of data in your 2-dimensional data or 2-dimensional matrix. Basically each element is a list, right? The number of list is 3. So we have 3 number of rows, and just pick any row because all rows are going to have same number of columns. So pick the first row and the number of element in the first row is going to be the number of columns. Now we are just going to do the processing from the first row and first column element, right? We are going to do the processing for these elements. We are not going to do the processing for the first row elements or the first column elements. But we know that the answer is going to be just take the sum of each element in your matrix, right? So initially what we can do is we can take the sum of the first row element and the first column element. But here you will notice that we are counting this particular element 2 times. So what we can do is we can say that let me count the first row and then let's count the first column, but don't count this element, right? Because we don't need to count it twice. And then we are going to do the processing for each element in the matrix starting from first row and first column. And simply we just need to check the upper, left and diagonal element, take the minimum of it, take minimum plus 1 and assign this element that particular value. And while assigning, we can just do the calculation as well. We don't need to run back the loops again. We can say that, okay, if it is a 1, then we are going to count 1. If it is a 2, we are going to count 2. So while assigning, we are going to do the counting as well. And let me show you the solution for this particular problem. It is very easy to understand. First of all, create a variable result, which is 0. As of now, the number of rows is the length of the matrix and the number of columns is length of matrix of 0. That is, take any row and that length will be the number of columns. Now let us try to process each element in the first row. So we are going to run a loop for C in the range of columns. And for each element in the first row, which is the 0th index row, we are going to say result will be equal to result plus matrix of 0 and C. That is 0th row and Cth column. So this is going to do the counting for the first row elements. Next, we are going to run another loop to do the counting for the first column elements, but we are not going to count the 0th row and 0th column element twice. So we are going to say for r in the range of 1 comma rows, we are going to count result is equal to result plus matrix of r comma 0. It means rth row and 0th column. That is basically the first column. Now once we have done the initial counting, we can just run a loop for r in the range of 1 comma rows and for c in the range of 1 comma columns. If the current element at index number r comma c, that is rth row and cth column, is 1, then only we are going to do the processing. We are going to find out the diagonal element, which is the matrix of r minus 1 c minus 1. Basically, if you are at row number 1 comma 1, then the diagonal element will be 0 comma 0, right? The left element will be matrix of r comma c minus 1. Basically the same row, the left element will be in the same row but one column behind, so r comma c minus 1. And the upper element will be r minus 1 comma c. Basically the upper element for this will be this particular one, which is one row behind and in the same column. So the upper element is matrix of r minus 1 comma c. Take the minimum of these 3 elements and your current element will be m plus 1, minimum plus 1, and the result will be result plus minimum plus 1 as well, right? Now you can return the value of result, and that is going to be a complete solution for this particular problem. Let me scroll a bit so that you can see the whole code. Now we can submit this and this is going to pass all the test cases. And the great thing about this particular solution is the memory wise it is really good. You can see the result. Memory wise it is very good. Runtime wise also it is good. Basically we are not using any extra memory. We are using the input array, the input matrix itself to store our answers as a memory for our dynamic programming table. So that space complexity is O of 1 and the time complexity is O of m by n. M is the number of rows and n is the number of columns. So we have solved this particular problem in a very efficient way. And that's it for this video, guys. If this video has helped you to understand the problem deeply and solve it in a very easy way, then make sure that you are hitting that like button. And if you have not subscribed to my channel, then make sure that you subscribe to the channel as well. And I will see you guys in the next video. I want to see you guys in the next video. Thank you for watching this one.